Thank you. I appreciate you pulling this up. Everybody can hear me okay?
Yeah.
Yeah.
Okay, great. Well, I'll try to run through these intro slides real quick just to catch up. But our
Okay.
project, what I'm going to be talking about is the our study of odor and corrosion for 168 kilometers of large diameter interceptor. So this project, this study was done in Oakland and Macomb counties, which is north of Detroit, Michigan. And there are 3 connected systems. I'll refer to them as the acronyms MID, OMID, and the Clinton-Oakland system, or COSDS. And if you go to the next slide, each one of these systems is managed by a separate authority. And even though they're separate, they have collaborated since 2011 to study odor and corrosions in their connected systems. The thinking being, well, what's happening in the upstream system is impacting what's happening downstream. And that's seen over the years, dating back to the early 1970s when they were constructed. They've had minor corrosion issues, some areas no corrosion, but in others they've had these serious deterioration that's resulted in sinkholes, as you see on the right, where interceptors collapsed. But since that time, you know, they've really taken a big effort in condition assessment, grouting, and relining, and studies like the one I'm describing today. So next slide, please. Now, the objectives of our study were to identify rates, ways to reduce the rates of corrosion, cost effectively extend the interceptor life, and also minimize odor complaints. So you can imagine with these large diameter interceptors, contractor mobilization is difficult, access is a challenge, and liner installation is complicated. And then you see, like here, an open cut installation where it's very disruptive to neighbors and not to mention very costly. So next slide. So this provides you with an overview of the 3 systems. On the west side is the Clinton-Oakland system. That basically flows west to east and ties in at the north end of the green system, which is the OMID. And as you travel further south, there's a connection to the MID, which is the red system. As all of that wastewater is collected and ends up at the southern terminus of these systems at the Northeast Sewage Pumping Station, that wastewater is lifted and ends up in the Detroit wastewater treatment plant. Next slide. So the MID and the OMID systems, those 2 are generally pretty similar in design. They're both larger diameter, reaching up to more than 3 meters in diameter. And flow is managed by a series of gate structures that are located throughout the systems. Most of those are in the OMID side of the system, but there's also a couple force mains in the MID. Community sewers contribute to these. Wastewater flows through metering structures. They discharge into drop manholes, and then wastewater ends up at the lower elevation, large diameter interceptor. Now, the Clinton-Oakland system is a little bit different. It's more extensive, smaller diameter sewers, and it doesn't contain flow gates, control gates like the others, but it does have a force main. Next slide. Now, these control structures are important. As I mentioned, they're mostly in the OMID and the MID systems. They're critical for managing sewer flows and for isolating portions of the system for maintenance or construction access. You can imagine if you take 2 drop shaft structures that have gates, you close them, you're actually able to isolate that section, dewater it, and then a contractor can access that and perform their work. But this happens at a regular interval too, daily basis. And they call this storage and release. Storage is when the gate is dropped. Release is when that, and in doing so, it stores wastewater on the upstream side of the gate. When you raise the gate, it releases that wastewater. You can imagine that turbulence releases a lot of H2S and causes corrosion. So we'll go to the next slide. And just very briefly, here's an overview. It might be difficult to see, but in the green section in particular, there's little dots that show where these gate structures are located, and they're basically at various intervals along the OMID alignment. And on the next slide, you'll see just a quick image of what one of these looks like. They're these deep shaft structures. They're about 70 feet deep in most cases. And in most cases, there are two gates, control gates, side by side in the interceptor opening. Next slide. So with a little bit of background on the system layouts, we want to talk about the tools that we used and leveraged to do a real in-depth study of this system. So the first one is historical data reviews, and that led directly into our sampling campaign. So if you go to the next slide, you'll see that we did both vapor phase and liquid phase sampling. Liquid phase was to characterize the wastewater, which we then used for our calibrating our sewer process model. Likewise, that vapor phase data capturing H2S levels and sewer pressures using acrologs, that was also really critical to sewer process model calibration. So we did this across 57 locations in across all three systems, and that actually occurred over about a 3-year period. So next slide. I'll talk briefly about air dispersion modeling, but basically what we were able to do here is we used it as a sensitivity analysis rather than as like a design tool, but we were able to model a typical manhole and a typical drop connection that had a gooseneck vent on it. And by evaluating against our odor criterion, we were able to identify the impacts, potential impacts to receptors that were 15.2 meters away. So if you go to the next slide, you'll just see that by doing a number of model runs at various H2S concentrations and pressure, we're able to develop a matrix that shows under what specific conditions we might actually impact that receptor and exceed our odor threshold. So we referred back to this matrix many times throughout our study. You know, when we got sewer process model results, we'd say, you know, if there's a certain pressure developed and we knew what that H2S concentration would be, we would have a pretty good sense of whether we would be impacting neighbors. Next slide. Partway through this process, we identified that vapor phase treatment would be a viable option. So we paired this with fan testing. So fan testing is a good empirical way to develop a few things. First, to identify your zone of influence, basically how far upstream and downstream from that extraction point you're able to maintain a negative pressure. You're also able to gauge with the additional dilution air that you bring into the system through ventilation, how that impacts H2S concentrations. That can directly impact what and help you decide what type of vapor phase treatment is appropriate. And then lastly, you're able to see directly what's the right sizing for that vapor phase treatment. And then lastly, we did sewer process modeling, which was probably the most powerful tool that we used in this process. We used megawatts and paired that with megavent to look at both sulfide transformations and then also what is occurring in the headspace. And very briefly here on the next slide in this chart, I won't be able to dive into all the investigated effects, but in a general sense, we're looking at the impacts of corrosion through sewer process modeling, the impacts of corrosion and odors, impacts of dry weather versus wet weather, maybe more concentrated wastewater and longer detention times versus wet weather, more dilute wastewater. We were able to look at specific things like storage and release, which is specific to these systems. We looked at forest mains and not only the presence of forest mains, but also the impacts of different pumping operations, pump sequencing, pump run times, pump cycling, things like that. And then we even looked at the impact of future rehabilitation efforts. So if a contractor has to enter into the interceptor to perform some work, that might happen more frequently than once a day or twice a day. And that obviously has an effect on the H2S that's released. So very briefly on the next slide, you'll see this is a good example of dry weather versus wet weather, where we show that dry weather or dry weather, this is a graph of the alignment of the sewer with corrosion. And you can see that we were able to identify hotspots of where corrosion might be the highest. And the next,
we've got about 3 or 4 minutes to kind of work it through.
The next slide has an example of a pump station. This was the Elizabeth Lake pump station in the Clinton Oakland system, where we looked at the impact of the wastewater going anaerobic in the force main. And obviously a lot of that is that H2S is stripped out of solution at the discharge. But we were able to see through the sewer process modeling that the high H2S, elevated H2S concentrations in the headspace actually extended further downstream. And that actually paired very closely with corrosion impacts, which were actually proven out by some of the sewer rehabilitation effort that another consultant was doing at the same time. And then lastly, the gate operation, you can see that in the black line, gate operation, you can see that in the black line, as you lower the gate, you build up that, raise that wastewater level on the upstream side of the gate. As soon as you start to open that gate up, that wastewater is released and has a lot of turbulence, and we actually modeled that the H2S concentrations as a result. And then lastly, on the last slide here, I'll just point out, you probably can't read some of that lettering, but that wording on the graphite mitigation approach. And when you're able to leverage these tools, you can prioritize projects better. You can identify mitigation approach. And when you're able to leverage these tools, you can prioritize projects better. You can identify proper system sizing, and then the best locations for treatment. So with that, I'd just like to acknowledge our partners on this, Oakland and Macomb counties, and say thank you.
Great. I don't see any questions. One question might be, when did you see frequency differences between winter and summer? And were you able to optimize the odor control based on seasonal conditions?
Yeah, we were. When we had our sampling campaign, inevitably some of the sampling that we did occur in winter. So we had a good data set for both cold weather and, midsummer conditions. And we were able to factor that into calibration of the model and capture those seasonal variations.
I have a question.
Yeah.
Dissolved sulfide concentrations, how did you measure those and track those? You mentioned acrologs for the gas phase, but liquid phase.
Yeah, for the liquid phase, we were using gas tech tubes. So they were grab samples of sulfide, but we also took whole wastewater samples and sent those to the lab for sulfate analysis yeah. Now we would maybe consider using something like a sulfologger for real-time measurement, which is something that we're also getting into on some of our other projects.
Yeah, I've seen some of the sulfologger data stuff. That real-time information is
effort to tie your model results to the dosing rates on any of the odor control strategies you did if you used liquid phase treatment?
Yeah, we actually didn't, in the current, actually the work that we did, we didn't work on a design of a liquid phase system as one of our upgrades. There is one that is being designed by others in the far northeast portion of the mid. That system I think is constructed at this point. But when we did our analysis originally and did the study and came up with ways to address odors and corrosion, we did use that data. We used the Watts model for dialing in what the dosing rates would be at that system.
Okay. So
that stayed in the study phase and was taken out by a different consultant during design and construction.
Okay, very good. I don't see any other questions. I appreciate that. Meeting our time problem with the delay on the slides. So I know it's always difficult when you're presenting, but appreciate it. Came out very clear, and thank you.